Hello, everyone. There was a question that I put on the holiday homework that I gave you guys that I realized shortly after writing it was possibly a little bit beyond your level of how to solve. So rather than just getting you to skip that question, what I'm getting you to do instead is to kind of like give like an abridged version of it, which is just to simply explain what does it mean for e to be an irrational number. Um, like what are the implications of that and what type of a number is e. And the purpose of this video here is to just kind of break down exactly what do we mean when we say a number is irrational. And I'm also going to attempt to give you a proof of why e is irrational, which is what the original question stated. And hopefully you can try and follow through the reasoning behind this video, even if there's never going to be a point this year where you're going to have to replicate this. So to start out with, let's just recap what exactly we mean by irrational, just by going over all of the numbers. So in maths, there are different types of numbers. Generally, the numbers that we talk about are first up what we call the natural numbers. So these are numbers like 1, 2, 3, 4. These are whole numbers that we can count, and they're also positive whole numbers. So these are the first numbers that people discovered when they were inventing numbers. So, for example, people might need to know how many sheep they had in a paddock. So they said, I have 3 sheep. They can count how many sheep there are. And at a certain point, it became necessary to talk about negative numbers and the number zero. In fact, from the invention of the whole numbers to the invention of the number zero, there was about a 1,000-year difference. I believe it was invented over in India. There's interesting stories behind that. I won't go into it here. But the next type of number that was discovered was what we now know as the integers. So this is usually represented with the letter Z. So these are the integers. These are basically all of the whole counting numbers, the positive counting numbers, but also the negative counting numbers, and also the number 0. So we can think now, okay, we have 0 sheep, so I don't have any sheep. I don't have any sheep in this room right now. But also, what does a negative sheep mean? Well, this might refer to debt. So we're negative, I possess negative sheep because I owe somebody a sheep. And then negative 15, so we can think like this is negative $15. I owe someone $15, or I've borrowed $15. Different ways of thinking about this. Okay, now the next type of number that became relevant, well, actually, I believe these were actually invented before negative numbers, were what we call the rational numbers. This is denoted with the symbol Q to mean quotient. So this is when we're talking about division. Now, rational numbers is particularly relevant to our discussion here. These are essentially numbers that can be represented as one number divided by another number, like a whole number divided by another whole number. So, for example, we could have, say, 2 over 3. That's a rational number. We could also have negative 15 or negative, I've written negative 11, so let's roll with that. Negative 11 over 9, whatever it might be. These are typically numbers we can write as one number divided by another number. We can also write these as a recurring or a terminating decimal. So, for example, we have the number 0.25 or the number 1.333, where the 3 is gone forever. These are all examples of rational numbers. And then finally, we have what we call the real numbers, which is basically all of the numbers that we can place on a number line. Those of you who do specialists know that there's then also complex numbers, but let's just restrict our discussion to this. So specifically, the number e sits within this category here. So it's a real number that cannot be represented as a ratio between two other numbers. So what that means is specifically about e, first up, let's get the notation correct here. E is an element of the real numbers, but e is not an element of the rational numbers. That is to say that e cannot be written as one number divided by another number, where a and b, in this case, are both integers. It's impossible to do this. So this means that e, its decimals are never going to repeat. There will be no repetition to the pattern, and also the decimals will never stop. So we have 2.71, we have decimals that go on forever, and they never stop. Okay, so how do we actually prove this? Well, that's the tricky question that I want to try and tackle right now. So now that we're kind of comfortable with the concept of what makes a number irrational, By the way, another tangent that I might quickly go down is there's different types of irrational numbers. There's what we call algebraic irrational numbers. And these are things like surds. So what I mean by that is the square root of 2, just like e, its decimals go on forever and they don't repeat. So this is what we call a surd. However, what we could do to the square root of 2 is just square it, and then suddenly we have a rational number. The thing about numbers like e and pi is there's no combination of algebraic operations that I could do. I can't multiply them by a whole number or times them by a whole number or divide them such that we can get back a normal real number. Unless, of course, you multiply them by 0, but that's kind of cheating. So there's no combination of standard operations that we can apply to these numbers to make them one of these standard rational numbers over here. So these are actually special types of numbers. They're special even among irrational numbers. We call them specifically transcendental numbers. So it's in the same category as pi in this respect. But right now, we're not really interested in that. We just want to show that e is an irrational number. Okay, so how do we do that? Well, again, what is going to follow up until now has been standard methods knowledge. What's going to follow in the second part of this video, you do not need to know. So I'm perfectly happy for you to just, in your answering of that question, just to give a quick little explanation of you can state e is an irrational number, it's a transcendental number, give a quick little definition of those two things, and explain what that means. However, what follows is a sort of an extension sort of idea. So before we come up with a proof as to why e is irrational, I want to talk about something else. And specifically what I want to talk about is geometric series. So this is kind of an aside or like a bit of a tangent, I guess. Geometric series. All right. So this is something that people who have studied methods will be familiar with. Now, geometric series is basically defined as a series of numbers that we're adding together, where each number in the sum is some multiple of the previous number, and that multiple is a constant. So I'll give you a simple example. Let's suppose we have 10 plus 1 plus 0.1 plus 0.01. Now, what we're seeing here, and let's suppose that goes on forever. What we're seeing here is a number. Every time what we're doing is we're adding 1/10 of the previous number. You might notice that 1 over here, the first number that I'm adding to that starting number is 10 times 0.1. And this next number here is 1 times 0.1. So it's the previous number times this common ratio of 0.1. So we're starting out with our starting number. Let's call this A. And every time we're adding that previous number multiplied by a common ratio, which in this case is 0.1. The next number is going to be that previous term multiplied by that common ratio. So the previous one in the sequence, in this case 1, and then we're multiplying that by the common ratio again. So it's going to be that ratio times the ratio again, so squared, etc. And in general, this is going to take us all the way down to, say, for example, the the nth term in this series is going to be a times r to the power of n minus 1. Where again, a is that initial number and r is that common ratio. So what we're going to find here is if we take this series, we're going to have, as you can see, an infinite number of terms in this summation. We want to somehow calculate what that number is, removing this infinite number of terms so that we can just type the numbers into our calculator and get an answer. So how can we come up with a general formula for this? Well, what we could do is we're going to do a little bit of an algebraic trick. So we're going to say, okay, we're trying to start out with this sum. So this sum is equal to the starting number plus that starting number times a common ratio plus starting number times a common ratio squared, all the way up to that starting number times the common ratio to the power of n minus 1. What I'm going to do is I'm going to take this series, I'm going to multiply the entire thing by r, and you're going to find that I come up with the following. So I'm basically going to take every single one of those terms in this summation, and I'm going to multiply it by r. So this first term here becomes a times r, the second term becomes a times r squared, third term becomes AR cubed, etc., all the way up to AR to the power of N. All right, and now what I'm going to do is I'm going to use what you might recognize as sort of the elimination method of solving equations. I'm going to take that second equation and I'm going to subtract the first equation. So we have RSN, take away SN. I'm going to go this term here, subtract this term, etc. When I do that, you're going to notice that a few of these terms are going to cancel out. Specifically, when I take this term here, and so when I'm taking this series, subtract this series, we notice that I have a times r minus a times r. They cancel out. A times r squared, take away a times r squared. They cancel out. This one here is going to be somewhere in this dot, dot, dot over here, all the way up to, before this one, there was an AR times N minus 1. That's also going to cancel out. And in the end, we're actually only going to be left with two terms in this series. This one here won't have cancelled out, and this one here won't have cancelled out. So RSN minus RSN is going to be equal to AR to the power of N minus A. So what I've effectively done here is taken this effectively infinite summation and I've simplified it down to a point where we can actually calculate it. So now we just need to rearrange this equation to find what this series is equal to. We notice that on the left-hand side, we can take out a common factor of that series. And now I can divide both sides by this r minus 1 term, and we find that a formulation for our series is going to be this thing over here. I'll take out the r and the a as a common factor as well. It's going to be this thing here divided by r minus 1. Cool. And another interesting result from this is if this series is infinite, and I'm going to write it with this notation here, then we're going to find that something else happens. So as n approaches infinity, and remember there's one way that we can write this is using limit notation, the limit as n goes to infinity of this thing, a times r to the power of n minus 1 over r minus 1, what is going to happen? Well, if this common ratio is, say, less than 1, we're going to notice that this term here, r to the power of n, is going to tend towards 0. So what do I mean by that? Well, let's suppose that r is 0.1. 0.1 to the power of n. Well, as n becomes increasingly large, this is going to be 0.1 times 0.1, that's 0.01. Or 0.1 times 0.1 times 0.1, that's going to be 0.0001. As n increases, this term tends towards 0. So this tends towards 0 in this limit, and everything else will go unchanged because nothing else contains n in this little formula here. So in the end, we're actually going to come up with the following. This thing becomes 0, so this is just going to be a times 0 minus 1, which just becomes negative 1, over r minus 1. And as we can see, that will just be equal to negative a over r minus 1, which we could also write as a over 1 minus r. Okay, so what I've now developed for you here is a formula for the sum of a geometric series, and you're going to see that this will become relevant later. Now, forgive me that little tangent. It is going to be important for the proof, so let's just sort of plug that to the side. And if you've just kind of zoned out up until now, maybe now is possibly a good time for you to try and keep following my reasoning here, because we're going to change tactics a little bit now. That's not going to work. All right, that's all good. Okay, so let's plug this for a minute. I'll just put this to the side as our interesting result. So this is equal to a over 1 minus r. All right, so now let's get back to the question at hand. We want to prove that. I'm going to write a proof that E is irrational. All right, using this information. Okay, so first thing that we need to know is the definition of E. So by definition, and I'm going to use one of the definitions that we explore in that investigation task, which is that e is equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, etc. What we can see here is that e is defined as this infinite series of factorials. You find this in one of the parts of the investigation where you need to approximate what e is equal to. A more concise way of writing this is that e is equal to the summation, so capital sigma, of n equals 0 right up to n equals infinity, where n is rational numbers, or sorry, integers starting at 0, counting up, of 1 over n factorial. So this notation is basically saying we're going to start out with 1 over 0 factorial, which is equal to, well, 0 factorial is equal to 1, if you don't remember. So therefore that's 1 over 1. So that's 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, etc. Okay, now the method of proof that I'm going to use here is something called a proof by contradiction. And the way that this proof works is we're going to assume that the opposite of what we want to show is true, and then we're going to use that to find that there's some issue with how we go about our reasoning. Those of you who've done specialist will understand what I'm talking about here. If not, just try and follow the reasoning. So to prove that E is irrational, I'm going to start by assuming that E is in fact rational, and I'm going to show that it's impossible for E to be rational, so therefore E must be irrational, right? So that's how we're going to do it. So let's start by assume that E is irrational. So therefore, by definition, right, because we've defined up here what a rational number is, it's a number that can be written as one whole number divided by another whole number. So therefore, E can be written as A over B, where A and B are integers, okay, by definition of a rational number. So let us assume that this is true. What can we find? Well, let's start out with our definition. So we have that, well, if E is irrational, I'll need to check how I did this before. Yep. So if E is irrational, that means, if E is rational, I should say, so we're going to assume that E is rational, therefore it can be written as E equals A over B. What we're going to find is if we multiply E by B factorial, we are going to get an integer. What do I mean by that? Well, if I take E, times it by B factorial, and if we accept that E is equal to some A divided by some B, notice that when I multiply it by B factorial, and if we remember B factorial means B times B minus 1 times B minus 2, etc., we're going to get A over B times B times B minus 1 times B minus 2, all the way down to times 1, for example, or times 2 times 1. We're going to see that this B here is going to cancel out with this B here, and here we're just going to have like an integer times an integer times an integer times an integer. If we times a bunch of integers together, we're just going to get an integer. So we see here that this thing is an integer. Okay? According to our logic here, if we accept that E is a rational number, then E times B factorial will also be a rational number. All right. So let's try and continue from this. All right. What we're going to do now is we're going to consider what would this thing here look like. So if we can see here, we have E times B factorial, right? And I'm just going to substitute in our definition of E that I've written up the top here, which is that E is equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus all the way down to whatever. In fact, I'm going to extend this series to a very particular point. I'm going to extend it all the way down to 1 over B factorial. Now, if we remember, B is it's just an integer, so this must appear somewhere in this factorial notation. B must be a positive integer specifically because we know that E is a positive number. So A factorial and b, a and b in this fraction over here, they must specifically be positive integers. So if we accept that b is a positive integer, which should follow from us accepting that e is rational, then we're going to have that b is going to appear in the definition of e. So, I mean, obviously this sum here goes on forever, so it's not just going to stop at 1 over b factorial, it is going to continue. So the next term will be 1 over b plus 1 factorial, next will be 1 over b plus 2 factorial, etc. So it keeps going on forever. That's how e is defined, as this infinite sum. All right. Now, what I'm going to do is something that's a little bit tricky. By the way, all of that, if we accept that e times b factorial is an integer, this thing here, e b factorial, is going to be equal to that, which is the definition of e, multiplied by b factorial. Okay, now I'm going to expand these brackets in a very particular way. I'm going to first expand this by multiplying b factorial by the first part of the summation up to here, and then I'm going to expand b factorial times the second part of the summation up to here. So if we split it like so, we're going to find that we have b factorial times 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial all the way up to plus 1 over b factorial. And then for the second half of the summation here, we have that b factorial multiplied by the rest of this sum. So 1 over b plus 1 factorial plus 1 over b plus 2 factorial all the way down forever. Okay, so what happens when I expand these brackets here? Well, the first thing that I want you to try and understand here is that this first part of the sum will be an integer. Now, why will that be an integer? Well, we have here b factorial, where b is some number. Now, in that b factorial, we're going to have, by definition, that will be equal to b times b minus 1 times b minus 2 times b minus 3 times b minus 4, etc., all the way down to times 2 times 1. After some dots there. So for example, 5 factorial, that's 5 times 4 times 3 times 2 times 1. You're going to notice that all of those smaller factorials actually appear within that expansion. So for example, if I was interested in 7 factorial, right? Like that's 7 times 6 times 5 times 4 times 3 times 2 times 1. And right here, that's 5 factorial. So I can actually write this as 7 times 6 times 5 factorial. And the reason that's relevant is if I was to distribute this b factorial term, I'm going to get, like, say, for example, over here, b factorial times 1, that's obviously an integer. This one here, b factorial divided by 2 factorial, well, there'll be a 2 factorial in the b factorial expansion that will cancel out with the b factorial down the bottom, and that will remove the denominator, leaving us with an integer for the numerator. So every single one of these terms, right down to b factorial over b factorial, which should just be equal to 1, every single one of those is an integer, okay? Now, if we accept that this whole thing, e times b factorial, must be an integer, which is what we set up here, right? So we said that when we take this a over b factorial, which we're assuming is equal to e, we multiply it by b factorial, we will get an integer, right? If we now know that this first part of the summation is an integer, that means that the second part of an integer, the second part of the expansion must also be an integer. Because if it isn't, then we have reached a contradiction. And that is what we must prove. So the second part of the proof, once we've got up to this stage, is essentially to try and show that this part of the expansion must also be must necessarily not be an integer, and then that will lead to a contradiction. Okay, so I'm going to pause the video here, and then in the second part, I'll show you exactly how to prove that. All right.